The last two geometries that we need to work through are 5 and 6 electron domains. So trigonal bipyramidal and octahedral. So we're going to work through trigonal bipyramidal first. So if I have 5 electron domains, the best arrangement in space is this trigonal pyramidal geometry. And so where did I come up with this? Right, phosphorus has 5 electrons. Fluorine, I've got 1, 2, 3, 4, 5 fluorines with 7 electrons each. Right, so 5 fluorines at 7 electrons each is 35 electrons. So a total of 40 electrons to assign. Here's 2, 4, 6, 8, 10 electrons there. And then now I've got 30 more electrons. Well, I've got 6 lone pairs on 5 different fluorines for 30 more electrons. The interesting thing about this trigonal bipyramidal arrangement is for the first time we have different bond angles within the same molecule. If I take a look at this structure, the central phosphorus to the fluorine, phosphorus to fluorine. And then I have my fluorines around the equator, the equatorial positions. So the two different bond angles are this. Between the axial and the equatorial position, I have bond angles of 90 degrees, right? The axis, the axial position, think of the Earth's axis, and the equator, the equatorial positions, the positions around the middle. For those positions, those bond angles are 120 degrees apart. So I've got two distinct bond angles. I've got 90 degrees from the axis to the equator, and then around the equator, each of those fluorine, phosphorus, fluorine bonds are 120 degrees apart. So that means there are two distinct locations within these geometries. So they are not chemically equivalent, right? They are not equivalent because my bond angles are different. So the axial positions, right, along the axis, and our equatorial positions along the equator. And so that's going to give us the two different bond angles that we observe with trigonal bipyramidal geometry. So let's work through a few examples of that. So the first example I've got sulfur tetrafluoride. So sulfur has 6 valence electrons, and I've got 4 fluorines at 7 electrons each for 28 electrons from fluorine. So I have 34 electrons to assign. So for the central atom, I have sulfur, and now I need to connect to 4 different fluorines. 1, 2, 3, and 4. So there are my 4 fluorines, and I used 8 electrons in that process. So I just assigned 8 electrons. I have 26 electrons to go. Well, let me fill the lone pair electrons for fluorine to give each of the fluorines an octet. So there's 1, 2, 3, 4, 5, and 6 electrons, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. So I just assigned 24 lone pair electrons on fluorine, filled the octet of each of the fluorines. I have 2 electrons remaining. Where does that go? That needs to go on the sulfur. So now, if I look at the sulfur, I have 5 electron domains. So with respect to my electron domain geometry, I am trigonal bipyramidal. However, of those domains, I have 4 bonding and 1 non-bonding. That would place me with a molecular geometry of seesaw. If we flip this 90 degrees, it would kind of look like a seesaw. So for the chlorine trifluoride, what would that molecular geometry and electron domain geometry look like? So for the chlorine has 7 valence electrons, my 3 fluorines with 7 valence electrons each. That's 21, 28 total electrons to assign. I'm going to place the chlorine in the center and assign my 3 fluorines. So there are 6 electrons I just assigned, 22 electrons remaining. I'm going to fill the octet of the fluorines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I have 4 electrons remaining. Where should they go? Well, if I look at chlorine, I only have 6 electrons on chlorine, and I've got those 4 electrons left. So 1, 2, 3, 4. Chlorine can break the octet rule, right? It has access to D electrons, so it's fine to assign more than 8 electrons to the central chlorine. And the other thing you'll notice too is I also assign those electrons around the equatorial position. So remember, these positions are not identical, the axial and equatorial positions. So when we replace a bond with a lone pair of electrons, we want to replace the equatorial positions first, leaving the axial positions. I did the same thing over here with the sulfur tetrafluoride. When I placed that lone pair of electrons, I placed that on the equator first, on an equatorial position first. So back to the chlorine trifluoride, I have 5 electron domains. 3 are bonding and 2 are non-bonding, so my molecular geometry would be T-shape. The last one, xenon difluoride. Well, xenon is one of the rare noble gases that actually can react. So it has 8 valence electrons, 2 fluorines at 7 each for 14 electrons, bringing my total to 22 electrons. So to assign those electrons, I've got my xenon, I've got fluorine, I've got fluorine. Now I've assigned 1, 2, 3, 4 electrons. I have 18 electrons left to assign. I'm going to fill the octet for fluorine. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 6 electrons left. Those need to go on xenon, and again, those go on the equatorial position. So 1, 2, 3, 4, 5, and 6. I still have 5 electron domains, so with respect to my electron domain geometry, I am trigonal bipyramidal. However, for my bonding domains, I only have 2 of those 5 domains are bonding, so my geometry, my molecular geometry, would be linear. The last part of that table covers the octahedral geometry, where we can have 6 electron domains. So let's take a look at sulfur hexafluoride and figure out that electron domain geometry, how that fits into the octahedral arrangement. So sulfur has 6 valence electrons. I have 6 fluorines in sulfur hexafluoride, so 6 fluorines at 7 electrons each, 42 electrons for a total of 48 electrons. I'm going to place sulfur in the middle. Now I have to place those 6 different fluorines surrounding the sulfur. So 1, 2, 3, 4, 5, 6. Each of those has 2 electrons each. There's 12 total electrons that I just assigned when I placed the fluorines around the sulfur. So that leaves me with 36 electrons to assign. I'm going to fill the octets of fluorine, so 6 fluorines with 6 lone pair electrons each. 6 times 6 is 36. So once I fill the octet of all of these fluorines, I should have assigned the remaining 36 electrons that I have in sulfur hexafluoride. Here I have 6 different electron domains. I still have the axial and equatorial position, but because I have 90 degrees from my axis to my equator, and now I have 4 positions around the equator, 4 equatorial positions, I also have a 90-degree bond angle here. So we are back to identical bond angles. All right, now I've got iodine pentafluoride and xenon tetrafluoride. Let's come together with the structure and the electron domain and molecular geometry for both of these. So iodine pentafluoride. Iodine, 7 electrons. I've got 5 fluorines at 7 electrons each for 35 electrons. That's a total of 42 electrons. I'm going to place iodine in the center, and I'm going to flank iodine with all of the fluorines. So I'm going to make it look like iodine. So there's 1, 2 electrons, 3, 4, 5, 6, 7, 8, 9, 10 electrons. I'll place the fluorines around, and I just assigned 10 electrons. I have 32 electrons left. Fill the octet of fluorine. So there's 6, there's 12, there's 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. So I have 2 electrons remaining. Those electrons need to be assigned to iodine. Iodine, again, can break the octet rule because it has access to d orbitals. So here are my 2 lone pair electrons assigned to iodine. So I have 6 electron domains. However, of those 6 electron domains, 5 are bonding and 1 non-bonding. So taking a look at that chart, right, if I have 5 and 1 non-bonding domain, I would have a molecular geometry of square pyramidal. For the xenon tetrafluoride, xenon, noble gas, 8 electrons, 4 fluorines at 7 electrons each. That's 28 electrons from the fluorine. That's a total of 36 electrons. Xenon in the middle, 1, 2, 3, 4, 5, 6, 7, 8. So I've assigned 8 electrons when I connected the xenon to the fluorine. That leaves me with 28 electrons. Now I want to fill the octet of the fluorines. So 1, 2, 3, 4, 5, 6. Here's 12. Here's 18. And here's 24 electrons I've assigned to fill the octet of the fluorine. So that's 4 electrons remaining. Where do those electrons go? Those electrons are going to go to xenon. Again, xenon can break the octet rule. It can have more than 8 electrons because it has access to d orbitals. When I take a look at xenon tetrafluoride, I have 4 bonding domains, 2 non-bonding, so a total of 6 electron domains, but because only 4 are bonding, my molecular geometry would be square planar. So what does this mean for larger molecules? All the exercises we worked through today and trying to figure out the electron domain and the molecular geometry, right? We can apply those same principles to larger molecules, always focusing on the central atom. So for example, acetic acid. Acetic acid is not flat like it's written here on the paper. Acetic acid actually does have 3-dimensional properties to it. But to do that, we need to analyze each of the central atoms and determine how many electron domains we have in that central atom. Based on that, how many are bonding and non-bonding, and then we can determine the geometry of each of those. So if I take a look and work my way through acetic acid, and again, only the central atoms really matter because they're what's connecting the molecule. If I look at this carbon, I notice this carbon has 1, 2, 3, 4 domains. So carbon 1, and all of those domains are bonding. So I'm tetrahedral at carbon 1. I'm going to have a bond angle of about 109.5 degrees. Carbon 2, let's take a look at carbon 2. So carbon 2, I have 1, 2, 3 electron domains. And so it's not actually as represented, right? Carbon 2 would be trigonal planar. I have 3 electron domains. All of those electron domains are bonding domains, so I would expect my bond angles to be about 120 degrees around carbon 2. So not the 180 as it's drawn here, but closer to 120 because of the 3 electron domains. Now, last but not least, we have our oxygen. So oxygen has how many electron domains? It has 1 bonding, 1 lone pair, so there's 2, 3, and 4 electron domains. So for my oxygen, I have 4 electron domains. Of those domains, 2 are bonding, 2 are non-bonding, so I would have a bent geometry, and I know my bond angles would be about 104.5 degrees. So now we can work through these molecules atom by atom, determining how many electron domains we have in each of those atoms, and then based on that, what would their electron domain and molecular geometry be? Because, as I said at the start, acetic acid is not a flat molecule as drawn here. It looks more like this, where I actually have 3-dimensional properties to that molecule, right? So here's my methane that was 109.5 degrees, my tetrahedral geometry. Here was my trigonal planar, where I was 120 degrees. And here is my oxygen, where I'm closer to 104.5 degrees, right? The Vesper theory will give us a very reasonable estimate of what those bond angles actually are. And again, this is only just something we came up with to help us understand and explain the geometries we observe. Right, so the important thing from today's lecture, 100%, you should be able to work through these steps. You should be able to, if given a molecule, draw the Lewis structure. After you have the Lewis dot structure, figure out how many electron domains do you have, how many are bonding, how many are non-bonding, and then based on that, what is ultimately not only the electron domain geometry of a molecule, but the molecular geometry of a molecule as well.